in the area unit, we talked about if I have two figures which I know are similar to each other, and I know the ratio of their sides. Let's say the ratio of their sides is 4 to 5. We call that the similarity ratio. If you know the ratio of two sides, what else do you know the ratio of? Anybody remember from last unit? If you know the ratio is 4 to 5, you know two other ratios. Anybody remember those? Frank, one of them? Perimeter ratio is also 4 to 5. You also know the area, but it's not 4 to 5. What do we do to find the area? Squared it. So the area ratio would be 16 to 25. Very similar, no pun intended, to what we're doing today, but we're going to talk about volume and surface area instead and how that relates to the similarity ratio. First thing, how do I know two solids are similar? One thing is, one condition it's got to follow is they got to be the same polyhedron. Meaning a cylinder and a cone can't be similar. A prism and a sphere can't be similar. They got to be the same polyhedron. And secondly, corresponding lengths must be in the same ratio. I know this is something we've gone over and over again, but now I just want to apply it to your solids, your three-dimensional figures. And I'm actually nervous to ask this because we've seen this how many times this year, similarity ratio. Can you describe to me what it is? Similarity ratio of two figures. How about that? If I get a little more detail, help me out, Juliana, please.
The proportion through which similar figures relate to each other.
It's the ratio of the two sides. You pick two corresponding sides. What's the ratio? We call that the similarity ratio. Anybody, another term we've called it before as well? Begins with an S. It's two words. One starts with an S. The other one starts with an F. Scale factor. Yes. Thank you for bailing me out, Madeline. Yes, scale factor. Just so you know, the abbreviation we use for similarity ratio, S1 over S2. That's the ratio of two corresponding sides. All right, are these solids similar or not? If they are, give me the ratio. Same polyhedrons? Check. Now I have to check, are the corresponding lengths in proportion? The same ratio. So give me two corresponding lengths. Let's start this off right with 97. Let's start this off right. Give me two corresponding lengths in those prisms. So is 7 over 4 the same ratio as, give me another pair of corresponding lengths. Here you go, 10. What? Oh, God. I have to get off this 11 train. I have to get off of it. I really thought I had this down. 18. Give me another set of corresponding lengths. 14 over 8. Same ratio as 22. 10.5 over 6. And just let's be aware, just because two of them might be in the same ratio doesn't count. All three have to be in the same ratio here for them to be similar. And how are you guys finding out if they're all in the same ratio? Finding their decimal equivalent. That's why you guys have calculators in front of you instead of just staring at me right now, waiting for me to tell you the answer. 7 over 4, 14 over 8, 10.5 over 6. Do they all reduce down to the same decimal equivalent? What are you finding there, 7? They all are. What's it reduced down to? Yep, 1 as a decimal 2, 1.75, right? Again, it's got to be all three. So yes, they are similar. And what would be my similarity ratio here? There are infinite answers here. Infinite answers you could put here. Doesn't have to be a reduced answer. One scale factor, you could tell me 27?
7/4.
Okay, 7/4. Anybody want to go 1.75 over 1, 14/8, 10.5/6? They're all correct. Okay, they're all correct. What about these two cylinders? Well, they're both cylinders, so that satisfies the first condition, that they're the same polyhedron. What ratios are you checking? 2. What ratio should I check here? 9/5. Is that the same as? What's the other ratio, James? 12/9. Yep. Same ratio? Nope. So these are not similar. So everyone all right on how to test if two polyhedrons are similar? All right, you got it. How to find the ratios now of surface areas and volume. How to find their ratios. That's the ratio of two sides. Do you think they're equal? If I know the ratio of two sides, would that be the same as the ratio of their surface areas? Take a while. What do you think? Yes or no? Same ratios? No. Surface area. Surface area. So what do you think I have to do to adjust this up here? Take my side ratio and do what with it? Square them. Yes, just like I used to do for area in the previous unit. And what happens if I'm already given surface area and want the side ratio then? I'm going to take the square root. Perfect. Volume. Think they're equal? Absolutely not. Suggestions of what do you think I need to do to the side ratio? And think of the units we always do. Cube both of them. Yep, cube them. And I'm going to ask this because we've worked with this already. What if I give you the volume and need the side ratio? Cube root it. Yep, cube root it. All right. By the way, you think he'll make an appearance today? Last show here. He'll make an appearance last show. Two cylinders, find me the similarity ratio. I'm already telling you they're similar. What do I give you here? What do I give you in the cylinders? What is that telling me? Oh, come on, 12. What am I telling you here? Surface area ratio is 49 to 81. But I want to know the ratio of their corresponding lengths. Like, what's the ratio of the heights? What's the ratio of the radii? It's not 49 to 81. What can I do with that 49 and 81 to find the lengths? 28? Take the square root. Let's do it. So their heights, their radii, anything I can measure that corresponds to each other will be in a ratio of 22? 7 to 9. All good. What about these two prisms here? You know the volume ratio is 125 to 512, but I need to know what the edge ratio is here. What ratio are their edges in? What are you going to do to the 125 and 512? 5? Cube root them. Everyone remember on your calculator, math, choice 4. To cube root, math, choice 4. What's the ratio of their sides, aka their edges? 27?
5/8.
Thanks. Everyone good? Because here's where we need to be in these next two problems. Read through here what I'm asking you. I give you the surface areas and I give you the volume of a larger figure. What's the volume of the smaller one now? Right now, what am I asking you to find? What's the ultimate question here? Find the what? Volume. Find the volume. So before you can find volume, I need to know the ratio of the volumes. All right, if I'm looking for the volume of the smaller one, I need to find what's the ratio of the volumes first. What's given to me? What ratio do you know? Surface area. All right, we need a plan here because if the surface area is 75 over 108, and you guys are telling me I need to get to the volume ratio before I find the volume of the smaller figure, how can I get from here to there? A plan, please. A plan on how to get from surface area to volume. Any plan here? 21, any thoughts? What's the 75 over 108, Luke? S 75 over 108. Surface area. What can you get me if you know the surface area? You can't get me the volume, but you could get me what in between here? The what? Yes, you can, the similarity ratio. How? Okay. So let's take square root of 75 over the square root of 108, put it in a darn fraction template, leave it as a fraction, please. $18, what do you got for me?
0.8. I put it in the fraction thing. It didn't.
All right, go to math. Turn it into a fraction. Yeah, you're better than that.
My calculator doesn't have a math button.
Does it turn into fraction, though?
What?
You should have a turn into the fraction. Fraction into decimal, decimal into fraction.
Okay, here it is.
Right.
I think I found it.
My calculator was weird.
Matches its owner. What is... Yeah, math. Fraction. Math, fraction. Matt, what fraction does it turn it into?
5, 6.
5, 6. Great job. 5, 6. But I need the volume ratio, so what do you want to do with the 5, 6? 4, what do you want to do with that 5, 6? Yep. So the ratio of their volumes will be 125 to 216. This is the ratio I want to use in the proportion now. So I'm going to take 125 over 216. Just remind me real quick, is this the volume of the larger one or the smaller one? The larger, so it's going to go with the larger number in the ratio. And this one, we should have changed the numbers around, but that's the way it ends up being. You can cross multiply if you want, but what's the smaller volume? 125 cubic centimeters. That will be a little different when we go to 6. But do you see what I'm saying with this? If I ask you for the volume of two similar figures, you need the volume ratio. If I ask you for the surface area, you need to give me the surface area ratio first. 2 minutes right now. Try out number 6 on your own. What'd you do with the 16 over 25? What are we doing with that one? 14, what are you doing with that one? What's that give you when you square root it? And gives you 4 over 25, which is your 4 over 5, which gives you your side ratio, your similarity ratio. And again, what am I going to do for volume? 12. What do you want me to do with 4 over 5 to get the volume? Cube it. So we're looking at, bless you, 125 over 64. That is what you want to use in your proportion right now. 64 over 125 is equal to, how do I use the 500 now? 25, how do I use the 500?
Wait, so you can put 64 over 125.
Which is the volume ratio.
I'm not sure.
Okay, is this 500 the volume of the larger or the smaller one?
The larger one.
The larger, so where should it go? Across from where?
Oh, it should go on the bottom.
Yep. And now I'm looking for the smaller one. And we're looking at 256 cubic inches. Are we okay here? If it asks for surface area, find the ratio first. If it asks for volume, find that ratio first. Oh boy, guys. Are you ready for the last problem? This is sad. We got a block of ice, kind of anticlimactic. A block of ice weighing 2 pounds. Another block of ice has dimensions twice as large. What's the new weight? Oh, it's 4. I'm done. No. You just don't double everything, including the weight. And I don't need you to do a fancy drawing. I'm just going to draw my block of ice here. And we got a bigger one that's twice the size. I don't know if this is really twice the size, but. Okay. When we are talking about weight, it's kind of like filling it up, right? Instead of talking about on the surfaces on the outside, when we're talking about weight, we are talking about the volume. Okay? When we talk about weight, we're talking about the volume. All right. We know it's not going to be 4 pounds. Any ideas on what I can do here based on what we've done today? Anybody know the similarity ratio? What's the side ratio here? I don't have to put any side measurements on there. I read the problem. What do I know the side ratio is? Carolyn? 1 to 2, 2 to 1, whatever we want to prefer. Yep, 1 to 2. There's the side ratio because I am doubling the dimensions. What is the weight of the smaller one? 2. And I'm trying to find the weight of the bigger one. But I have a problem right now in my proportion. I have a problem. That's the weight, right? Which is another way of saying the volume. Side ratio equal to the volume ratio? No. Anybody want to adjust my proportion? Frank? Cube your similarity ratio. Yes, cube the side ratio. And you will see it's a lot more than doubling the weight, right? How much does this bad boy weigh? How much? Yeah, it's 8 times as much. Weighs 8 times as much. Go ahead, Skylar.
Why does the weight mean volume? I thought it would mean mass.
Well, it does, but remember, the mass too is like, say I fill up an object, like I'm increasing the mass of it. So, and remember, inside, the space inside, that's volume.
Because you're doubling the dimension.
Not just doubling the dimensions, just when I talk, and I'm not done yet here. When I'm talking weight, I'm thinking about inside the figure, right? And if I go inside the figure, that's not surface area, it's going to be volume. Okay, so that's how I weight to volume. Okay, and this is not good enough for me just to show you guys this. I want to actually show you something you are very, very familiar with and why it ends up being 8 times the size. Cubes. Give me a dimension on one. Good. Any dimension you want. 4? You got it. Mean I'm doubling and it's going to be 8. How would you find the volume of that cube? How would you find the volume of that cube? 4 times. 4 times. Go ahead. That's going to be 64, right? All right. Volume of this doubled cube. 8 times 8 times 8. Go ahead. What's the volume of that double size cubed? 512. Anybody know how many times 64 goes into 512? How many times? 8. That's 8 times the size of it. Okay, so when you double the dimensions, all right, you don't get a cube that's twice the size. You actually get a cube that's 8 times the size. And where's that 8 come from? Cubing the similarity ratio. Okay? We all good there? Great. I am done with new stuff. Congratulations. Honors geometry. You're done with the curriculum. We're not done with the day, though. You know where we're going right now. Not only to a Regents question, a proof. Why not? End the week on a great note right now. Yep. Fake me as you walk out. Yep. End it on a great note. No. Proving AE congruent to CF. When I see that, you guys know CPCTC. Before I can go CPCTC, what's got to be proven congruent first? 2 triangles. So I'm going to just take a look here. And I really don't know how many different ways this can be done, but the first way I'm thinking of, I pick a triangle that's got AE in it, and I pick a triangle that's got CF in it. And I'm going to try to prove them congruent. What type of figure is ABCD? Quadrilateral. No properties. No properties. It's a quadrilateral. It's got 4 sides. Angles add up to 360. That's all you can really use, which we're not going to use in a proof. AB congruent to CD. These are parallel as well. And I got some perpendicular lines going on as well. Okay, it's a quadrilateral as I'm talking to you now, but now that I put those markings on, anybody know what magically it becomes? Rico. Yeah, buddy, it's a parallelogram. Anybody know why he knew it was a parallelogram? Madeline. Our little special case. Remember, if you have one pair of opposite sides congruent and parallel, that tells me that bad boy is a parallelogram. Did we see that at all? I know I'm going quick here, but I want to make sure we get done with the proof. But did we see that? Was it already a parallelogram? Okay, good talk. All right, now that it's a parallelogram, you can go property crazy. And I still got those right angles hanging out. So you can go a couple different ways, wherever you want there. Wherever you want, number 11. How do you know that, Amanda? Yes, it does. All right, so Amanda got you guys a pair of sides in those two triangles. That's the only thing we have written down is a pair of sides right there. That's it. Where else you want to go? Try to get those, remember, trying to get those triangles congruent. We can do it. We can do it. 8, next. Let's say, yep. Okay, they are. You're right. Why is that, Ethan? Okay. Could help us. We'll find out. Does it give us a pair of congruent parts? No, but it may help us. I don't know. We'll see. 4, where do you want to go? Let me just mark them so everyone sees. He is saying that angle, and that is 100% correct, because what type of angles are they, Skylar? Yes, and I couldn't say they're congruent until Ethan said they were parallel, so it did actually matter, believe it or not. Yes. Okay. So angle DAE is congruent to FCB. Parallel lines imply alternate interior angles congruent. That gives me a pair of angles. All right, it looks like I need one more pair of something. And you guys got it. You got it. 18, you got it.
DA and CFB are right.
Good job. Got to say the right angles before they're congruent. Angle DEA and angle, what else? CFB. Oh, you've missed doing these, I bet. Why are they right angles there, Matt?
Because perpendicular lines imply right angles.
It's like you guys never left. And now say they're congruent. And then I'll ask somebody why the triangles would be congruent. All right, give me a solid method here. You got it. Why is triangle DEA congruent to triangle CF? Did I get those in the right order? I'm not even looking at the diagram. DEA should have been BFC. Got a method there for me? 1, not here. Yep, great. But well, it's which, by the way, why don't we have a 1?
Because, well,
Wasn't there a kid that used to be here when he left?
And he was 1? I didn't know the origins between why there was no number 1 when it's literally the first number somebody says when we go around and pick our numbers.
Yeah, no, there's the kid that sat.
Yeah. Okay. There was, yes. There was. You're correct. There are no longer 2 former members of the class that were with us first day of school, I believe. So.
Wait, was he a freshman?
I have no idea. Literally, like, okay, and I hate to, like, this is going to be really bad, and I apologize, Todd, because it's about you, but I had no idea you were a sophomore until I walked by Mr. Lewis's room and saw you in that AP World class. I had no idea. Like, there's so many sophomores, like, I had no idea until about third quarter that I had so many. But, yeah, whoa, we didn't even go over, what's the way? Angle. If somebody just said angle, 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 you better leave. Angle, angle, side, and then CP, CTC, yes.